So now that we've got a governing equation for hydrostatic situation, we're going to go ahead and apply it to at least one condition. So the first condition we're going to study is a condition when rho, the density, and g are constant. That, of course, makes this equation fairly easy to integrate. So we can go ahead and look at how that would work. We're going to take multiply both sides by dz, so we get dp is equal to minus rho g dz. Then we can integrate both sides of that. We have an integral here, integrate here, and we get our integrals. And then because rho and g are constant, if we want to go through the grueling detail of this, it would be integral on the left is just dp. Integral on the right would be minus rho and g, because they can come out of the integral because they're constant. And so we have simply the integral of dz. The integral of dp is, of course, p. The integral of dz is z. We'll integrate from a state 1 to state 2, or position 1 to position 2. And so we'll just have P2 and P1 on the left-hand side. P2 minus P1 is equal to minus rho g, Z2 minus Z1. So that gives you us our equation for a constant density and constant gravity. We can calculate pressure changes as a function of height changes or position changes in the height direction. Often in the past, you may have seen this as the change in pressure is equal to minus rho g times the change in height. So as that height gets higher, your pressure gets lower, or if, of course, your height is actually a depth, then that's a negative delta H, and your pressure increases as you go deeper into a fluid. As an example of an application of this, a very straightforward example, we'll take a look at water. So we know that P atmospheric is 101,000 newtons per meter squared. And so we're going to ask, at what depth underwater is P equal 2 atmospheres? So at what depth underwater does the pressure, I'll call it P2, equal 2 atmospheres? So that's what we're looking for. When does the pressure equal 2 atmospheres? So as you go in the water, obviously the pressure increases and increases as you go deeper. And we're going to now ask, when does it go to double normal atmospheric pressure? We know that water has a constant rho. We've talked about this multiple times in this class. So for almost all conditions, we can treat water as a constant density fluid because it is so highly incompressible. So that makes this a good situation to use this equation for, because this is the situation for constant density fluid. And G also can be treated as constant. One could ask, how high and low do you have to go? G is not actually constant. Gravitational acceleration does depend on the distance from the planetary center. But for those of you who've taken my dynamics class, we prove that you could go up even to airplane heights without appreciable changes in G. You really only have to worry about variables in gravity if you're doing space-based type engineering, which we're not doing right now. We're going underwater, not into space. So we're going to draw this up here. We've got a surface of water up here. I know that the pressure at the surface of the water is 101,000 newtons per meter squared. I'm going to go down to some depth here, call it D, which is going to be under the water. Here's the water. And I know the pressure at this depth, I know it's going to be minus P0 is equal to minus rho G H, H, but H is equal to minus D. So that's going to be minus rho G minus D as my equation. So if you want to do P as a function of D, is going to, minus P0 is equal to plus rho GD. Common sense check here. The pressure under the water better be higher than the pressure at the surface. So if this equation doesn't give me higher pressure, I did it wrong. This does give me higher pressure. My pressure at D is going to be greater than my pressure at P0. So P at D is going to equal some P0 plus rho GD. Pretty simple. I know all the values, the pressure I'm after. I want this P sub D to be 202,000 newtons per meter squared. That was my target depth. I wanted one where I have 2 atmospheres of pressure. I have the P0 is 101,000 newtons per meter squared. That's atmospheric pressure. And then I've got rho, which I know is 1,000 kilograms per meter cubed, because that is the density of water. I know that G is 9.81 meters per second squared, because that's what gravity is. And I'm after D, my single unknown. I've got one equation, one unknown. I can solve that. I have D is equal to 101,000 newtons per meter squared divided by 9,810. My units then are kilograms per meters squared second squared. When you do the multiplication out, D comes out to be 10.3 meters. So that's the answer. If you go 10.3 meters under the water, you will find that the pressure is twice regular atmospheric pressure.